Hello, my name's Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering. And this is Module 18 in my Computer Networks lecture series, where we talk about IP addressing. And this is one of my probably favorite modules to teach in this section of the course because, sorry, I'm just getting my pen color right here. Understanding IP addressing is a big chunk of just understanding the magic of the internet in general. Like, how is it possible that your computer sitting in your house can send or receive a message from any other computer located anywhere in the world? So part of the answer is routing tables that we talked about in the previous module, where all of the routers have these tables that they maintain. And when they receive a packet, they look at the destination address in that packet, look that address up in their routing table and say, aha, I have to send this packet along, my third network interface, for example. However, there's a lot of unanswered questions. First, and as we sort of highlighted at the end of the last module, is it necessary then for every router to have an entry for every single possible destination on the internet in order to be ready for any possible packet? And the answer is no. And the way that we get around that requirement is using something that we refer to as hierarchical addressing. And a great way to understand hierarchical addressing, its benefits, how it works, is to use an analogy with the postal service. And so to kick off this module, I'm going to work through a bit of a postal service analogy where let's assume that we are located in Calgary, Alberta, in Canada, and I want to send a letter to my friend in Australia. And I'm going to just sort of step through how that works, and I'm going to point out certain aspects of the postal service that are shared with the internet. And we'll go through this analogy and keep it once we're finished this analogy, keep it firmly fixed in your mind, because thinking of the postal service as we get into talking about actual IP addressing will really help you understand how the internet works specifically. And so for this example, let's say that I have a friend who lives in Townsville, Australia, and I write a letter to my friend, which is very quaint. I mean, not very many people write paper letters anymore, but let's say that I do that. And on the front of my letter, I put the full address. So my friend lives at 99 Fulham Road in Townsville, a town called Townsville, which is located in the province of Queensland in Australia. And this, by the way, there really is a Townsville in Australia. And I drop this letter into the mailbox on my street in Calgary. Now, the first thing that's going to happen is, at the end of the day, the letter carrier is going to come and open up the mailbox and take out my letter and take a look at it. Now, at this point, the letter carrier doesn't even really need to look at the address, because the letter carrier has a certain default behavior, and that is basically just gather up all of the letters and take them to the postal sorting facility in Calgary. And so they're taken to the Calgary post office. Now, you can imagine in the Calgary post office that we have all kinds of letters coming in, and at some point a letter sorting staff person pulls our letter out of the bag and takes a look at it. Now, is it necessary for that letter sorting person in Calgary to know that in Australia there's a province called Queensland. In Queensland there is a town called Townsville, and in Townsville there's a road called Fulham Road. It's not, right? All that letter carrier, or sorry, all that letter sorting person has to do is take a look at the country portion of the address written on the envelope. The letter person looks at that and says, oh, this is for Australia. And the letter is then put into a large mail sack destined for Australia. So at that point, the letter sorting person in Calgary does not look at the province, the town, or the road. All that person has to do is take a look at the country, and based on just the country information, the letter is put into a big bag, and all the letters destined for Australia are put into the big bag. Whether they're going to Perth or Sydney or Townsville or wherever, all the Australia letters are put in a big bag. They're loaded on an airplane in Calgary. That airplane takes off and it flies, across the ocean to a post office or a letter sorting facility in Sydney, Australia. Let's say that's where sort of the Canadian international mail is received. And so at this point, the letter sorting person in Sydney, Australia opens up the bag of letters from Canada. And of course, all of these letters are destined for Australia. That's why they're in Australia. So that letter sorting person in Sydney will not really need to look at the country portion of the address. Now, is this the place where we finally meet somebody who knows that there's a road called Fulham Road and a town's called Townsville? Not necessarily. So the letter sorter in Sydney really just has to look at the next level of the address, and that's the province. So the letter sorting staff person can see that this letter is bound for the province of Queensland, and as a result is dropped in the big bag that leaves the Sydney post office on its way to Brisbane, which is the capital of Queensland. So even in Sydney, in the actual country of Australia, the letter sorting person at that first point of reception doesn't have to know all of the details of all of the towns and all of the roads. It just needs to now distribute the letter based on the next level of the address, which is province. The Queensland bag then is loaded onto a truck probably, or perhaps another airplane, and is delivered to Brisbane, which is the capital of Queensland. And again, we have another letter sorting facility. And at that facility, the sorting staff people don't have to look at the country because they know they're in Australia. They don't have to look at the province because they know they're in Queensland. This is the point where we start to look at the next level of the address, which is the town. So the letter sorting staff person in Brisbane is aware of all the cities and towns in Queensland and will distribute the letters according to the town or city level of the address. So the letter sorting person in Brisbane will take a look at the fact that this letter is destined for Townsville, drop it into the Townsville bag, and that's it. The letter sorting staff person in Brisbane doesn't need to know that there's a road called Fulham Road in Townsville. They just need to know that the letter is going to Townsville. Now, the Townsville bag is probably at this point dropped on a truck, driven to the actual town of Townsville, where it finally gets to the Townsville postal office. And this is where the letters will be given to individual letter carriers, staff people that will actually take the letter and deliver the letter to a house. And it is at this point that we need to have knowledge of the specific roads within Townsville. That knowledge will be contained by the letter carriers, and the letter carriers will be able to take the letter, say, oh, this is for 99 Fulham Road, and we'll take it to the letter's final destination. Now, in many ways, perhaps this has been an obvious example. People, you don't have to think too hard about knowing, being aware of how the postal service works. However, I want to point out a couple very key pieces of information that are going to be leveraged when we, sort of translate this analogy into the internet. The first really, really important point about this example is how the letter uses a hierarchical address. And by that we mean we indicate first the country, which is very broad, the province, which is a little more specific, the town, which is a little more specific, and then finally the specific house number on a specific road, which identifies the exact destination. Because we can use this hierarchical type addressing, this frees the letter sorting staff people from having to know all the detailed, specific geographical knowledge of Australia. So the staff person in the Calgary post office doesn't need to know that there's a province called Queensland. It doesn't need to know there's a town called Townsville. They don't need to know that there's a place called Fulham Road. All they need to know is that there's a country called Australia, and all the letters for Australia go into one big bag. Same thing when we get to Sydney. The letter sorting person in the Sydney post office is not looking at the country anymore, but doesn't need to know that there's a little town called Townsville in Queensland. The Sydney staff person certainly doesn't need to know that there's a road called Fulham Road. All that staff person needs to know is that there's a province called Queensland, and all the letters for Queensland go into one big bag that are then sent to Brisbane for further sorting. It's not until we get to the letter carrier level, just before we deliver to the final destination, that we encounter a node or a person with actual detailed knowledge of all the roads in Townsville. But this letter carrier can store that information because all the Townsville letter carriers have to know are the road and address information within Townsville. So a letter carrier from Townsville does not need to know the roads in Calgary because they don't deliver letters in Calgary. They only deliver letters within Townsville. So once you get down to that final level where you do need very specific knowledge of final destinations, again, this knowledge is manageable because the nodes that operate at that point are only in charge of a relatively small area. Again, sort of leveraging that idea of hierarchy. And this is basically how the internet works. We have hierarchical addressing used on the internet, and that frees the routers, which serve basically the same purpose as the letter sorting staff people along this chain. The routers are kind of like the letter sorters. And a router in Calgary doesn't need to know the specific locations of all the computers in Australia. All it needs to know is that this packet is bound for Australia. It has one default behavior for all packets that go to Australia. It sends the packet along that route. And so rather than having one entry for every single computer in Australia, it basically just has one entry for the entire country. And that's how we make routing tables a lot more manageable. So really the rest of this, if you understand that concept, you essentially understand how the internet works, which is, I think, pretty cool. The rest of what we're going to talk about in this module are basically just kind of the details of what IP addresses look like and how they implement this kind of hierarchy. So to kick off our discussion of IP addresses, I want to start by taking a bit of a historical perspective. And so there were a number of versions of IP addressing, but sort of the The one that's still relevant today is IP version 4. And IP version 4 addresses are still used. So this isn't historical in the sense that they're not used anymore, but there are some aspects of IP version 4 functionality that have since evolved. So an IP version 4 address is 32 bits that's usually written in 4 single byte chunks separated by using a dotted decimal notation. And so, for example, the IP address for the University of Calgary website is 32 bits long, and we express it as, the first byte dot the second byte dot the third byte dot the fourth byte. So the address is 136.159.37.42. And then obviously each of these numbers between the dots can't be bigger than 255 because they only represent 8 bits. And so IP addressing, like the the addresses we use on letters, does have a hierarchy. And IP addressing started out with a simple 2-level hierarchy. We had a network ID to indicate sort of the big network that we were, where the computer was located, and a host ID which identified the specific host in the network. And originally, there were 3 types of IP addresses: Class A, Class B, and Class C. Class A had an 8-bit network ID, so the first byte was to identify the network. The remaining 3 bytes indicated the host on that network. Class B used a 16-bit net ID, so half of the address was to identify the network, the other half indicated the host. And Class C used a 24-bit net ID, so only the last byte was used to identify hosts. So, for example, the Class C network could only have up to 255 hosts. And the University of Calgary has an old Class B type network where the network ID is 136.159, so the first 16 bits of the address, and then the host ID is 37.42. And host IDs are not unique, but net IDs are. So there cannot be another Class B address with a network ID of 136.159, but 2 Class B networks can have host IDs of 37.42. For example, we could have an IP address that's 102.126.37.42, right? So this is the network ID part, that's unique, and the host ID is not unique. Kind of like in 2 different cities, we could have a main street, for example. So there could be, a house at house number 42 on Main Street, and we could have that both in Calgary and another city. But because the city names are different, we're not going to confuse them when we deliver letters to them. Okay, so now let's do an example that demonstrates how even just this very simple 2-level hierarchy makes things a little bit easier for the routers on the internet. And so let's take an example where we have a packet that is addressed to IP address 192.168.1.18. And it needs to be delivered to its final destination, which I'm circling down here. Now, at the start of this example, the packet is entering into this first router. Now, just like in our previous module, when a router receives a packet, it takes a packet, looks at the destination address for the packet, and then looks that address up in its routing table, and the routing table tells it what network interface to send the packet out on. And so the difference with this example and the one in the previous module, however, is that the routing table now doesn't have a separate entry for every single possible destination. Instead, the routing table has an entry for each network ID. And so the router doesn't bother looking at the host ID. Instead, the router just looks at the network ID 192.168 and finds the entry in its routing table for 192.168. And so this notation is basically trying to say that any address that starts with 192.168, regardless of the host ID, is sent out on network interface 0. And so the packet is sent in this direction. This is exactly like the Postal Service example. When the letter sorting staff person in Calgary brings in the letter, it looks at the country and based on that country information drops the letter in the Australia bag. It doesn't look at any of the rest of the address. Just based on the country, it's able to know what to do with the letter. By a similar token, just based on the network ID, this router knows what to do with the packet. And we now only have one entry in our routing table for that entire network rather than having an entry for every single computer on that network. So if we continue to follow the example, we end up in a second router. That router again will take the packet, look at the destination address, but then only look at the network ID on portion of that address. It will look up the network ID portion in its routing table. It will have one entry for that network ID. And the routing table says that every packet with the network ID 192.168 is sent out on Ethernet interface 2. Now, we finally arrive at our third router, which is actually in charge of the local network 192.168. So this router you can think of as kind of the letter carrier level of the network. Once we get to this final third router, this is the router that has the detailed street level knowledge, if you like, in order to find specific machines on the network identified by 192.168. And so this router will receive the packet, take a look, first of all, at the network ID and say 192.168. Hey, that's my network. It is possible that this third router might receive packets for other network IDs, in which case maybe it has another network interface and it would send that packet onto the next network. But because it recognizes this packet as being addressed to the machines on the network it's responsible for, it will then proceed and do local delivery. And so it knows that it has a computer with IP address 192.168.1.18 on its network, sends it through an Ethernet switch to its final destination. Now, I mentioned that IP addressing has evolved somewhat. And the first way that IP addressing changed as the internet started to grow was to introduce a concept called subnetting. And subnetting was essentially meant to address a problem with the original sort of three categories of networks. So you'll recall we had the Class A networks, Class B networks, and Class C networks. And it was kind of like a little bit like sort of a Goldilocks and the Three Bears problem where, one bowl of oatmeal was too hot, one was too cold, and then the third one was just right. That's sort of what happened to IP addresses, because it turned out that Class C addresses weren't super useful because they only allowed 256 hosts because they only had 8 bits for the host ID. And most organizations that were, or a lot of organizations that were, started to use the internet very quickly had more than 256 computers within their organization. However, at the other end of the problem, Class A was also unpopular since very few networks had, this is a little bit of a typo. This should be 2 to the 24 or 16 million hosts. So for Class A networks, we have 24 bits for host IDs, which is about 16 million hosts, and that was a lot of hosts. Class B addresses, on the other hand, were a much better fit. There was, they had about the right balance between network ID and host ID space, but there were only 65,000 of them because there's only 16 bits allocated for the network IDs. And so there weren't very many Class B addresses available, and they very quickly started to run out. And so the concept of subnetting was basically to kind of get a little bit more flexible in terms of how many bits we allocated for the network ID and how many bits we allocated for the host ID. So essentially subnetting allowed us to allocate an arbitrary number of bits to the network ID, and the subnet is essentially used to indicate how many bits correspond to the network ID. And so the subnet is basically a 32-bit mask, and if you do a bitwise AND with your IP address and your subnet mask, you determine or you extract the network ID. And to be more specific about that, let's say, for example, we wanted to use the top 12 bits of the IP address for our network ID. What we would do then is we would have a subnet mask that would be 1, equal to 1 in the first 12 bits. Or if we wanted to use dotted decimal notation, our subnet mask would be 255.240.0.0. We would then, when we received an IP address, if we wanted to extract the network ID, we would take the IP address and do a bitwise AND with our subnet mask, which of course would extract only the top 12 bits and would zero out the remainder of them. So if a packet with address 150.100.15.11 arrived at our edge router, we would AND with our subnet, and then we would extract only the top 12 bits for our network ID, which would be equal to 150.96. And so with the introduction of subnetting and the notion that we can have a variable number of bits assigned to our network ID, very quickly afterwards, the concept of classless interdomain routing, or CIDR, was introduced. And CIDR is basically the routing scheme that removes the distinction of being class A, B, and C, and allows routers to route packets using network IDs that are variable length. Now, because we no longer have these three classes of networks, it became necessary when indicating a network ID address to also indicate in our notation how many bits were used to represent the network ID. So for example, if we are using an 8-bit network ID and our network ID is 136.0.0.0, and those last three zeros are there because we're not using them in our network ID, we actually still do have to indicate in our notation that we are using just 8 bits for our network ID. And we do that by writing a slash and then the number of bits used for our network ID. And the reason for that is because it's not enough to just zero out a portion of the address and then assume that that is, only the non-zero bits are part of our network ID. Because, for example, we could have a 16-bit network ID where the first byte is 136 and the second byte is 0, but that 0 is part of a valid network ID. And so now when we're using CIDR and we're indicating a network ID, we always have to use the slash to indicate how many bits are being actually used for the network ID. And so now we have all this flexibility. We can have a variable number of bits assigned to network IDs, and this kind of raises the question, okay, well, who's in charge of all of this? Who's coordinating all of this? And internet address space is centrally organized and coordinated by an organization called the Internet Assigned Numbers Authority, or IANA. And the IANA has its own website, www.iana.org, which actually contains the IP address space mapping for all the different countries and organizations in the world. Now, this is a big job, so the IANA often assigns chunks of address spaces to what are known as regional internet registries, which are responsible for a region or country. So for example, there is a North American regional internet registry, which is known as ARIN, and the mapping within ARIN can be looked up on www.arin.net. So I would really encourage you to go onto the IANA website, go onto ARIN's website, just to kind of see what information is up there. But part of the functionality on these websites is to be able to look up specific IP addresses and see what sort of big address space blocks the IP addresses come from. So for example, you can look up your own IP address for your home machine and then look it up on ARIN, and you should see that it belongs to a big chunk of addresses that have been given to your internet service provider, maybe Shaw or TELUS, and that big chunk belongs to another larger chunk of IP addresses that have been given to Canada as a country. And you can kind of see the hierarchy. I should make kind of an important distinction here because, at the very start of this lecture series and at various points along the lecture series, I make a big deal about how one of the advantages of the internet is that it's fully distributed, right? So there's no sort of central control entity deciding how packets are routed across the network, for example. All of those routing information or all of those routing decisions are made, in a decentralized way by individual routers using only local information. There's no sort of central controlling node like there was with the old telephone system. However, when I talk about the IANA and ARIN, it does seem all of a sudden like there is a central controlling authority, but there's an important distinction. So the only thing that is being centrally controlled is how addresses are assigned and distributed across the internet. So there is a central authority that says, okay, here's a block of addresses that Canada gets to use. Here's a block of addresses that Australia gets to use. Here's a block of addresses that TELUS gets to use, and then TELUS can decide how to use their block of addresses to assign it to their customers. However, the IANA does not decide how packets are routed from TELUS to, a computer on Australia. The actual sort of route finding and packet forwarding decisions are made in a truly decentralized fashion. So that's an important thing to remember. And the final point I wanted to state is that some IP addresses are not meant to be, or are reserved for machines that are not publicly addressable on the internet. Or directly reachable on the internet. So for example, the 16-bit network ID 192.168 is reserved for private local area networks that are protected behind a firewall and are not, assigned to publicly addressable computers that are reachable directly on the internet. So for example, if you look at the IP addresses that your sort of at-home, wireless router or firewall assigned to the computers within your house, chances are those IP addresses are going to start with 192.168. And your publicly reachable IP address is going to be the IP address that TELUS assigns to the other side of your firewall. And so to kind of, sort of conclude this discussion, let's do a little bit of an example. Let's take a look at the hierarchy of the IP address 136.159.12.134. This is a University of Calgary IP address. If you look up this address on the ARIN website, you will see, first of all, that the first byte, the first 8 bits of this address, belong to an 8-bit network ID that has been assigned to Canada. So the network ID 136.0.0.0/8 is a block of IP addresses that are assigned to Canadian computers. And you can think of this as kind of the country level hierarchy in our address. So if a computer in, let's say, Brazil wants to send a packet to Canada, it could start out with an IP address. Let's say it wants to send a packet to 136.159.12.134. A router in Brazil is not going to have any information beyond this 8-bit network ID. And so it'll have an entry in its routing table saying all packets that start with an 8-bit network ID 136 are Canadian packets, and it will just send that packet along some big network interface that is like some big fiber optic trunk that runs from Brazil in the direction of Canada, probably via the United States. And so that's kind of our country level address. The city level is basically the 16-bit network ID assigned to the University of Calgary. So again, on the ARIN website, you should be able to see that the 16-bit network ID 136.159 is assigned to the University of Calgary, right? So you can think of that as kind of the next level of our hierarchy. You'll note that, you know, the country network ID is basically contained within the 16-bit network ID that is assigned to the university. And that, you know, when a router in Canada at the edge of the network for Canada receives a packet, it will look at the network ID 136.159 and will send it along some large trunk destined for the city of Calgary, for the University of Calgary. Once the top level University of Calgary router receives that packet, it will then look at all of the network IDs it has created within that 16-bit network space. So for example, it may have created, the University of Calgary network designers may have created a subnet that uses a 25-bit network ID that is equal to 136.159.12.128. And we'll send, based on that network, we'll see that this IP address contains that 25-bit network ID. So it will send the packet to that subnet within the University of Calgary. Maybe it's the engineering network. And then finally, the remaining bits, I guess the last 7 bits will indicate the specific host computer. The host ID part, the last 7 bits of this address is equal to the number 6. And that indicates the actual computer that we are trying to reach. And you can think of this almost as the house number, right? So this is the final level of the hierarchy. This is sort of the house number. And so just to recap that, this is our overall address. The first 8 bits of the address assigned by ARIN indicates the country. So all 136 addresses are part of a big block assigned to Canada. The first 16 bits, so including the country portion, but then adding another 8 bits on, are part of the big address block assigned to the University of Calgary. Then within the University of Calgary, maybe the first 25 bits, So including the 136.159 and then adding 9 more bits on top of that. The first 25 bits of the address could then be used to identify a specific subnet. So that's kind of like the street level. And then the final host ID is the actual house number that allows us to deliver the packet to a specific spot. And finally, just a quick word about IP version 6. So IP version 6 is now being used more and more on the internet. I'm not going to say dive into a ton of detail on IP version 6. Actually, most of the examples I'm going to do in this lecture series use IP version 4 just because it's a little bit easier to write, and IP version 4 is still certainly very relevant. Also, IP version 6 and IP version 4 are functionally pretty similar with just a few enhancements. So the primary advantage of IP version 6 is that there's a longer address field. So IP version 6 has 128-bit addresses rather than 32-bit addresses. And this solves the problem of the world essentially running out of IP version 4 addresses. So 32 bits is not enough to address all of the computers that we have in the world. We've been able to get around some of the problems by reusing IP addresses or using these private networks, these reserved addresses like, the 192.168 addresses to, address all the devices within individual houses. But even with kind of reusing IP addresses behind firewalls, we still were running out of IP addresses. So IP version 4 fixes that. With 128-bit addresses, we can accommodate 3.4 times 10 to the 38 hosts. So plenty of address space now. The address space is still broken down between network and host IDs using CIDR notation. So that functionality is certainly still the same. The packet format has been simplified a bit. There's a simpler header. We've removed the CRC, so this actually isn't a CRC, it's the internet checksum. We've got extension headers, so we can add new information in a flexible way to the headers to support different network functionality, different sort of giving different packets, different levels of treatment as they travel over the internet to support different quality of service requirements. Packets can just be bigger, so we can send much larger packets over the internet if we want to, in order to get more efficient transfers for a certain amount of overhead. And we also have something called flow labels, again, to sort of manage packets that have different traffic requirements or different quality of service requirements. So there's a lot of additional functionality. IP version 6 is certainly important. It's being used more and more on the internet. Certainly in your working lifetimes, you will see almost a complete transition to IP version 6. But like I said, I'm going to stick with IP version 4 for teaching purposes, just because it still is very widely used, very commonly used on the internet. And the functionality is quite similar between the two.